Welcome back to part 10 of Password Cracking 101+1. In the last video we finished off on a combinator attack where we looked at generating combined word lists from a single one and then using that in combination with itself to look to attack 2, 3 and 4 element passphrases. The example of which here shown was a 3-element passphrase without a delimiter. So, moving on, we are going to look at a couple of other attacks before we build into the next exercise. The first one isn't so much an attack, more a technique that is very, very useful in nearly all situations and should generally be used when attacking passwords, particularly with rule files, and that's called a loopback. So --loopback, just tack that on to the end of your hashcat session, and what that will do is it will take all of the previous cracks or the plain text cracks you've got from your existing session and then feed that back into hashcat and rerun your attack again with rules over those newly generated planes. So we can look to do this in a couple of ways. You could use something like awk to go through your hashcat pot file. Your pot file is your file that contains all of the previously cracked passwords that you've had in hashcat and create a word list out of it. So to look at everything you've cracked in the past, create a word list out of that, for example called potfile.list, and then run that with a rule with loopback. And what that will do is it will go through and do something like this. This is an example where we've not used a pot file, but we've just added on a loopback to like a new cracking session. It will go through your hash list using your dictionary, your rules, and in this example we've cracked 6,405 passwords here. That will then restart when it's finished. You can see here this is exhausted. So hashcat then restarted, it ran through again, and I've truncated the screenshot to fit it on the screen here, but a further 4 passwords cracked, bringing us up to 6409. When that exhausted, it then reran again and cracked another one before exhausting a final time, and we didn't get any more. So what this means is you've gone through your hashcat session, you've generated a load of candidates based off your mangled word list, and then when it's done, those new passwords that you've cracked are then fed back in and the rules are reapplied to them, generating yet further permutations of those candidates. So as long as if there are lots and lots of passwords in your hash list that are kind of similar or form off base words that have just been permeated in several different places, loopback can catch a lot of these by feeding your planes back in and then rerunning the rules over on top of them. Okay, Expander. This is a great tool that can do crazy things with your words to generate some very unorthodox passwords. It's part of the hashcat util suite. It doesn't come with hashcat by default, so you need to download this. But this splits your password candidates, mutates and reconstructs them. Now it's interesting to note that Expander by default will only do this with 4 characters in your with whatever word list you give it. So in this example here, look, we say we're echoing the word hashcat into Expander. We then need to unique it because it will produce duplicates, and we're just looking at the top 10 in this instance, and you can see it's slicing up the word hashcat in different places, starting from different places, but it only takes up to 4 characters. It's always worthwhile just going into the C code and recompiling this for a length 8. So as you can see, you get a lot more bang for your buck there, and you'll be able to get a lot more letters out. And you can see the type of thing it's doing. It's starting the word, in this case hashcat, that we've given it at different places and then going up to 8 characters ahead from there. So for longer words you can get lots of different slices of the word. You'd be amazed at sometimes how many weird and wonderful candidates this can create, and again over large hash sets you can really get some good wins with this. So run Expander, give it a word list to expand of course, or a pot file, and then unique it, and then the result might be something that you want to feed into hashcat. Now Expander forms the basis of an attack called the Fingerprint attack, which has been around for a long time, and it's detailed on the wiki, but I still feel like it's largely kind of largely unknown, which is a bit of a shame because it can be a really, really nice attack when other dictionaries and rules and things have failed you. This is kind of a nice self-perpetuating attack because it can run with 0 word lists. You don't need to give it anything. I mean, you can do, but you don't need to give it anything. What this does is, this uses Expander to expand your previously cracked passwords. Okay, so basically, looking inside your hashcat pot file for everything you've cracked previously, expanding that, and of course uniquing it, and using that to create a word list. Then using that in a combinator attack with itself, and the results of that are then stored in a new word list. So as we can see here, and we'll go through this in an upcoming exercise, awk-f is using a field separator of colon, and what this is going to do, the printnf, is going to print the last field, the last column effectively, of our hashcat pot file. Now in the hashcat pot file, the last field we're going to get is the clear text password. We will see this on the terminal shortly, but what this is doing is taking effectively the clear text passwords from our pot file, and then we're piping that into Expander, uniquing it because it will produce duplicates, and then creating a word list from it. We're then taking that and running it in hashcat in attack mode 1, which is combinator mode, against itself, so word list and then word.list again, as you might have remembered from an earlier video. Anything we crack from that, store in a new file called word.list2. From here, it's a repeat and rinse. We then take word list 2, the new cracks that we've just got, expand them out, unique them, create word list 3, and then run word list 3 in combo with itself. What you'll find is particularly suited to large hash lists, but you'll crack lots, and then it will peak, and then it will very quickly tail off into nothing. So there'll be kind of a curve you see with that, until you reach a point where you either get nothing, or you feel like the diminishing returns are enough that it's not really worth your time investment running it each time. The remove just removes hashes from the file as we're cracking them each time, so that you're looking at less every subsequent hashcat session. Okay, let's take a break from hashcat and jump into Kerberos Auth, because why not? We are going to be looking at attacking a Kerberos hash in the upcoming exercise, which is why we are looking at this now. Now, the condensed title on this slide doesn't even close to do it justice. Kerberos is an absolute beast, or should I say Microsoft's implementation of Kerberos. But hopefully we're going to boil this down into something that's kind of understandable, especially with regards to a particular attack which is very pertinent in Kerberos, even in modern day environments. So we have our client, which is us, and we have a domain controller, okay? And what we are going to do as a client is ask for access to a service. Now there are lists of services that we can look at, and we'll touch on a list in a second, but I always use SQL Server in this example. So we're the client and we want to gain access to a SQL Server host on the domain. We say to the domain controller, can I please have a ticket granting ticket, a TGT, okay? And we send this request to the DC. This is called the AS-REC stage. We're not going to dig into too much terminology within this. We're going to keep this as high level as possible. The DC then decrypts and verifies my message, and if I'm a valid user, if I'm a valid domain user, it will send me back a TGT, a ticket granting ticket. Now I have this ticket, I'm going to send it right back to the domain controller and say, thank you very much, can I please gain access to SQL Server? And for this I'm going to need a service ticket, or a TGS ticket. And this is the ticket I'm going to ultimately use to authenticate to SQL Server with. The DC then says, okay, thanks very much. It creates this service ticket, or TGS ticket, but interestingly it encrypts it with the service account's NTLM hash and sends it back to me. And we'll come back onto this in a second. I then take this ticket and try and authenticate to SQL Server with it, in this instance. And it's at this point where SQL Server will then either allow me access or not. Now, at no point during this exchange between the client and the domain controller does the domain controller have any idea of whether I'm actually allowed access to SQL Server or not. It's just concerned with whether I'm a valid domain user or not. So any domain user can request these service tickets for services, specific services, not every service, specific services on a domain. Any domain user, irrespective of whether they're allowed access to it or not. Now, because these service tickets are encrypted with the service account's NTLM hash, we can grab these tickets, take these TGS tickets offline, extract the hashes, and try and crack them. And if we can crack them, we can get access to the underlying service account that powers said service. So this is really, really powerful, because all you need is valid domain credentials. And this attack is called Kerberoasting. Okay, it's been around for a long time. I think Tim Medin pioneered this, might have been 2014, but it's still a very, very popular attack in modern day environments, and for organisations that do have a number of service accounts where domain users have been configured to run these accounts. This is not uncommon to see, and it's very often an easy way to move on a network, to gain administrative privileges, and do a number of other things. So when these domain accounts are configured to run as a service, something called a service principal name, an SPN, is created, and this maps the service to the host as shown here on the right. This is a screenshot from Active Directory, and we can see here we've got a service, and we have a service principal name set down here. Now the format is shown as here. We've got our service identifier followed by the host and the port, which is just the structure it takes. But in this instance, the SQL Server is run by this account here, SVC MS SQL 10. Now it's this underlying service account that's used here. So it's the NTLM hash of this account that's used to encrypt this TGS ticket that we can take offline and crack. So if we're able to crack that, so that, yes, this does mean again we are at the mercy of a weak password, or at least a semi-crackable password, we could authenticate to the SQL Server as SVCMS SQL 10 and potentially elsewhere on the network, depending on the privileges it has. Okay, so just once again, this is a really powerful attack because we only need valid domain credentials to do it. We don't actually need access to any of the services we're requesting tickets for, and therein is the real beauty of it from an offensive perspective. So, into the next exercise, we are going to do a fingerprint attack against this curb hash shown here. So the first thing I'm going to do is have a look at this curb hash, because it's a huge hash, as you can see, much bigger than any of the things we've looked at so far. We can see we've got some like Kerberos identifiers here at the top, and this is for the SVC MS SQL 10 account here on the inseccorp.local domain. Okay, so Kerberosing tools will extract these really big hashes that we can take offline and try and crack. The next thing I'm going to do actually is show you the hashcat pot file, because we haven't looked at this yet, but I've spoken about it a couple of times. This is a file that by default will store everything you've cracked with it, to date in hashcat. So if we have a look at the pot file, we can see here evidence of what we've done so far. We have our first Linux hash here with the clear text Star Wars at the end. Here was our NTLM, Bigfoot Sunshine, so on and so forth, our brute force, our hybrid attack, so on and so forth. Now, we just want to take these clear text passwords that we've cracked so far, and for those of you who've done lots and lots of password cracking on Hashcat, you'll have huge pot files with loads of really useful plain text passwords that you can use to do this. We only want these ones. Now, you could use something like cut to do it. For example, you could cut on a dollar delimiter, not a dollar, sorry, a colon delimiter, and you could try and grab things like that. We could extend the field to make sure we capture everything, but there are sometimes problems with doing this, because if we're looking on a colon for a delimiter, not every hash is a very simple one, like NTLM, for example, where we just had a hash colon field, colon password. So because some of these, for example, the cache domain creds, for example, here, had several colons in, we need to make sure we're extracting the right one, and as a result there's the awk command that we've referenced here in the slides. So this is a bit of a cleaner command. I'm not ever saying take everything on blind faith. If you've got some really crazy, weird and wonderful hashes in your pot file, it's always worth checking just to make sure you've not got any junk data. But this will do a better job, rather than cut, of ensuring it just grabs the last field delimited by a colon from your pot file before we then feed that into Expander, and or do whatever we want to with it. Okay, so with that in mind, let's expand our word list. Here's the command from the slide. We're going to look inside our pot file, separated on colon, this field separator. We're going to look for the last field as defined here and extract that out. We're then going to pipe that into expander.bin, and then we're going to unique the output and create a word list that we're going to call word.list. Oh, once again, I should really make sure that I'm in the right place. There we go. So, extracted the planes from our pot file, expanded it, uniqued it, created a word list. And if we now look at word lists, word.list, you will see evidence of the expander tool we showed on an earlier slide. As you can see, it's chunked up to a length of 8. All of the different passwords, and you can see evidence here. This was our combinator attack. Look, about, caught, applying, or whatever combination it was. At 6 monsters is here from earlier videos, so on and so forth. So now that we've got that, we can look to attack that in a combinator mode with itself. So we're going to call hashcat. The mode we want for Kerberos is mode 13100. It's a TGS reply, okay, it's a TGS rep ticket. And we are going to attack our file in A1 combinator mode, combining word list with itself, and we're going to run optimized kernels because why not? Look at that, and it cracked instantly. And there we have the clear text password at the end. So quite a crazy password there, admittedly. Not necessarily saying this is, this is going to be the all-unifying attack that breaks everything, it cracks everything. Of course, it's not. Passwords are passwords, and some people do actually just choose really, really robust passwords. But a fingerprint attack is definitely something that's worth looking into, especially if you've got a nice big pot file where you've got lots of options there for expanding and uniquing your previously cracked clear text passwords to generate some really crazy, weird and wonderful candidates. And if you do crack that, of course, and we're talking about a large cracking session, you can then take the output of that file and then repeat and rinse the process and see if you get any further still using this fingerprint attack. So there we have it. Again, all these answers are built into the Kali machines in the Kali /.answers folder. There's a hidden folder called answers inside the Kali directory, and that has all of the questions and answers that we're covering so far. But with that, thank you very much, and look forward to seeing you in the next video.